Good evening, Professor Darren. My name is NACHUAN. Today, my topic is overdamped pendulum model. So here we go. First, I'd like to share my agenda with you today. In the first place, I will give a short introduction, and after that, I will talk about overdamped pendulum model in details. Now, let's talk about introduction. So far, in previous chapters, we've concentrated on the equation x dot equals to fx, which we visualized as a vector field on the line. Now it's time to consider a new kind of differential equation and its corresponding phase space. This equation, let's go to the next page. Yeah, theta dot equals to f theta, corresponds to a vector field on the circle. Here, theta is a point on the circle, and theta dot is the vector, a velocity vector at the point determined by the rule theta dot equals to f theta. Like the line, the circle is one-dimensional, but it has an important new property, which is by flowing in one direction, particle can eventually return to its starting place, just like this figure. Yeah. So thus periodic solutions become possible for the first time. To put it another way, vector fields on the circle provide the most basic model of systems that can oscillate. And in all other respects, flows on the circle are similar to flows on the line. Okay, so today I'm gonna talk about overdamped pendulum model. And here we go. We now consider a simple mechanical example of a non-uniform oscillator, an overdamped pendulum driven by a constant torque. Let theta denote the angle between the pendulum and the downward vertical, and suppose that theta increases counterclockwise as follows. And from what I have mentioned earlier, the Newton's law yields the equation 1, where that in this equation, m represents mass, and L is the length of the pendulum, B is a viscous damping coefficient. You can also call it a friction coefficient, and G is the acceleration due to gravity, and gamma represents a constant applied torque. Well, in particular, and all of these parameters are positive, apparently, and in particular, when gamma is bigger than 0, implies that the applied torque drives the pendulum counterclockwise, as we have mentioned before in this figure. Yes. And it is readily apparent that the equation 1 is a second-order system, but we can approximate it by ignoring the ML 2 dot theta term under an assumption that B is sufficiently large. And in this way, we have equation 2, which B theta dot plus mgl sine theta equals to gamma. By dividing mgl on both sides of this equation, we can have the following equation. To think about this problem physically, you should imagine that the pendulum is immersed in molasses. The torque gamma enables the pendulum to plow through its viscous surroundings. And please realize that there is an opposite limit from the familiar frictionless case in which energy is conserved, and the pendulum swings back and forth forever. So in the present case, energy is lost to damping and pumped in by the applied torque. And now we have the, after dividing mg on both sides, we have the equation as follows. So if we let tau equals to mgl over b multiplied t, and gamma equals to tau over mgl, then we have that theta prime equals to gamma minus sine theta, where theta prime equals to this. And now we need to do a classification. To the dimensionless group gamma is a ratio of the applied torque to the maximum gravitational torque. If gamma is bigger than 1, then the applied torque can never be balanced by the gravitational torque, and the pendulum will overturn continually. The rotation rate is non-uniform, since gravity helps the applied torque on one side and opposes it on the other. And as gamma goes to 1 plus, the pendulum takes longer and longer to climb past theta equals to pi over 2 on the slow side. And when gamma equals to 1, a fixed point appears at theta star equals to pi over 2, and then splits into 2 when gamma is smaller than 1. And on physical grounds, it's clear that the lower of the two equilibrium positions is a stable one. And as gamma decreases, the two fixed points move farther apart. Finally, when gamma equals to 0, the applied torque vanishes and there is an unstable equilibrium at the top, inverted pendulum, and a stable equilibrium at the bottom. Well, I have finished my presentation, and this is the end. Thank you for your time, Professor Darren. Thank you.